Directed connected graph G. Directed connected graph G. Containing loops. Containing. 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 No loops is called. No loops. No loops is called network. It's called network. Network. Called network N. If and only if. And only if. And only if. And only if. There are two distinguished subsets. There are two distinguished 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 subsets of vertices S and D. Subset of vertices. Subset of vertices S and D. S and D. S and D. Called source and sink. Source and sink. S is the source, D is the sink. Source and sink. Source and sink. Source and sink of N respectively. N respectively. Second, there is non-negative integer. There is non-negative integer. Non-negative integer valued function K. Valued function K. Defined on edge of G. Defined on edge of G. Edge of G. Defined on edge of G. The function K is called capacity function of G. Function K is called Fn means function. K is called the capacity of function of G. The capacity function of G. Fn means function of G. Capacity function of G. And E is the edge of G. E is the uh, edge of G. E is the edge of G. Is the edge of G. E is the edge of G. Is the edge of G. Value edge of G. The value K of E is called capacity of E. The value K of E is called capacity of E. Capacity of E. Capacity of E. We think K of E is representing the maximum rate. We think we think we think K of E representing the maximum rate of the rate which a commodity can be transported along E represent the maximum rate represent the maximum rate maximum rate maximum rate at which commodity can be transported along E. Each commodity commodity which commodity can be transported along E can be transported 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 along E along E transported along E. Vertices which are neither source nor sinks are called intermediate degree is zero. Intermediate vertices. Intermediate vertices. In general, in transport network, the sources have the in degree zero and sink D has out degree. Out degree is zero. Then when we represent a network by GK, mean that G is the underlying directed graph of the network and K is the capacity function defined on edges of G. Defined on edges of G. Defined defined edges of G. Page number 208. Number 2. Example. Page defined. Example, page number 209. Example. phase 209. Consider the network flow instead of the network flow. Network flow. Consider the network flow shown in below figure. Observe that the figure below, below. Observe that there is a zero flow. So there is a zero flow. Zero flow. Observe that there is a zero flow into the source S. The source S. Source S. Along the edge of edge. Along the edge. Along the edge. B comma S. B comma S. B comma S. For each intermediate. For each intermediate. Each intermediate diagram. D. S is the sink. S means source. D is the sink. D is the sink. Next. D, E. E. Next. And aromatic is there. Aromatic. This is the this is the so S has outsourcing. S is the arrows are out degrees. There is there is one in degree. One in degree. So next here. Here thermal here also thermal. It's in degrees. This is directed. This is graph is known as directed graph. Directed graph. So A, B, B, C, D, E, B, A, B, C, D, E. Here 2 comma 1, and 2 comma 1. Here 6 comma 4, 6 comma 2. Here 5 comma 2, 5 comma 2. Here 10 comma 2. Here 3 comma 2, 2 comma 2, comma 2. Next, here 4 comma 1, 4 comma 2. Next, here 2 comma 1, here 4 comma 4, 3 comma 2, here 3 comma 1. So what is S? Here, vertex X, X, X. The flow into X is equal to flow out of X. X, vertex X. Let's listen. The flow into X is the flow into X is equal to flow out of X. Flow out of X. Good. For example, easy means example. The flow into the vertex E, the flow into the vertex E, vertex E, vertex E is f of A comma E, f of A comma E plus f of C comma E, C comma E, C comma E. That equal to 2 plus 2 equal to 2 plus 2 AE CE, 2 plus 2, 2 plus 2 that equal to 4. 4. While the flow out of E, while the flow out of E, out of E, out of E, out of E out of E is F E comma D. E comma E comma D plus F E comma small d. E comma small d. That equal to 2 plus 2. 2 plus 2. That equal to 4. 2 plus 2. That equal to 4. We note that the flow along edges S comma D along the flow along edges along edges along edges S comma A S comma A. These are all from diagram S comma A and A comma E and A comma E A comma E A comma E is actually equal to the capacity. Actually is AC TUA LL by A LL by actually equal to the capacity. Equal to the capacity. Capacity. Equal to the capacity. Thus these edges are thus these edges are edges are thus these edges are saturated. These edges are saturated. 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 While all other edges while all other edges all other edges while all other edges while all other edges all other edges while all other edges while other edges while all other edges while all other edges while all other edges while all other edges are unsaturated unsaturated saturated unsaturated unsaturated. If an edge is unsaturated, if edge is unsaturated, 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 unsaturated. Then we define the slack of V. Then we define that. Then we define, then we define and define slack of E, slack of E, slack of E, inflow F, inflow, inflow, flow F, inflow F to S of E will be S of E, S of E equal to K of E, K of E minus F of E, minus F of E, minus F. For example, the slack of edge E, comma D, the slack of edge E, comma D, edge E, comma D. D means sink, E, comma D. That equal to 8. That equal to 8. And the slack edge D, comma D. And the slack edge slack edge E, comma D equal to 8. The slack edge D, comma small d, comma capital D, that equal to 2. So also the flow out of sources, yes, the flow out of sources, yes, sources, yes, sources, yes, equal to f of s, comma n, f of s, comma n, f s, comma n, plus f of s, comma c, f of s, comma c, f of s, comma c, that equal to 4 plus 2, that equal to 4 plus 2, that equal to 6, that equal to 6. And this in turn, and this in turn, in turn, in turn is equal to flow into sink D, equal to flow into sink D, flow into sink D. One definition we discussed, and also we discussed an example. Then theorem, page number 210. Page number 210. Theorem. Number 210 theorem. Page number 210. Theorem. Statement. Let G comma K be, let G comma K be a network and yes, a network, a network, be a network, be a network, and S and D. S and D, S and D. Be its source, it's a source, P its source and the sink respectively. Sink respectively. RES respectively. Yes, PLY means respectively. Then the flow out of S. Then the flow out of S. Of S. Flow out of S. And the flow out of S. That equal to F of S. F of S, comma V of G. V of G. That equal to F of V of G. That equal to F of V of G. F of V of G. F of V of G. Comma D. Comma D. That equal to the flow into D. Equal to the flow into D. Flow into D. Flow into D. Flow into D. Proof. Here proof. Proof. So we observe that F of V of G. We observe. We observe. We observe. We observe that that F of V of G. F of V of G. F of V of G. 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 X belongs to V of G. X belongs to V of G. F of X comma F of X comma F of G. F of G. That equal to sigma X belongs to V of G. X belongs to V of G. F of V of G comma X. V of G comma X. That implies equation number 1. By condition 2. Right? Condition 2. By condition means condition of the definition 2. From definition. So F of X comma V of G. X comma V of G. V of G. V of G comma X. X comma F of V of G comma X. V of G comma X. V of G comma X. V of G complex. V of G complex. For all x belongs to. For all x belongs to P of G. P of G. That means S, comma D. That means sink. S is the source, D is the sink. So thus above sum becomes thus the above sum becomes sum becomes above sum becomes f of s comma v of g s comma v of g s comma v of g plus f of d comma v of g f of t comma v of g v of g that equal to f of v of g v of g v of g comma s comma s plus f v of g v of g s v of g comma d comma d. This is equation number 2. But we know that but we know that f of v of g. But we know that we know that f of v of g f of v of g f of v of g comma s that equal to 0 that equal to f of v of g comma f of v of g v of g v of g of v of g f of equal to 0 f of v of g comma d comma d. Therefore, there is no flow into S and no flow out of D. That means no flow into S, no flow into S, no flow into S, no flow into S, and no flow out of D, and no flow out of D, no flow out of D, no flow out of D, no flow out of D. No flow out of D. So by theorem 12.0, we have f of s comma v of g that equal to f of v of g comma d hence proved Next. Next definition. Next definition. It's hence proved. Hence proved. Definition. A flow F in network. A flow. A flow. F in a network. F in a network. F in a network. G comma K is called maximum flow. G comma K is called maximum flow. K is called maximal flow. Maximal flow. Maximal flow. Maximal flow. If mod f, if mod f is greater than or equal to mod f1, mod f1 for every flow f dash, for every flow f dash, every flow f dash, every flow f dash in G comma K, G comma K. Thus f is maximal if the value of f flow. Thus a flow f flow f flow f is maximal is maximal is maximal is maximal if the value of f value of f the value of f value of f value of f is the largest possible value is the largest possible value possible possible value largest possible value largest possible value largest possible value of any flow of any flow any flow example example page number 211 page number 211 example we will illustrate the procedure for finding we will illustrate the procedure 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 illustrate the procedure for finding the maximal flow for finding the maximal flow finding the maximal flow with a simple network simple network simple network simple network shown below shown below shown below. So here diagram in you shown below. Here diagram. Next one. Yes, this is the source. D is the link. A, here A, B, here C, here D, B. Here 4, 3. Here 2, 2. 2, 2. 2, 1. 2, 1. 3, 1. 3, 1. 1, 1. 1, 1. 4, 2. 4, 2. The value of any flow, the value of any flow, the value of any flow on the network, on the network, on the network, mod f, that equal to f of s comma a, f of s comma b plus f of s comma b, f of s comma b. We have f of s comma b, s comma b, s comma b less than or equal to k, less than or equal to k, s comma b less than or equal to b, less than or equal to b. That means f of s comma u, s comma u, that equal to f of a comma d, a comma d plus f of a comma s, a comma s, a comma s less than f of a comma s, a comma s, f of a comma s. We have is less than or equal to f of s comma a comma d, and a comma c, s, a comma c, a comma c, a comma c. A comma d, a comma d, a comma d plus k a comma c, a comma c, that equal to 1 plus 2, that equal to 3. Therefore, mod f or mod f that equal to f of s comma a plus f of s comma b, s comma b less than or equal to 5, less than or equal to 5. Hence this flow is maximal. Hence this flow is this flow is maximal, maximal. Hence flow is maximal. Next, cuts and minimal cuts. Cuts and minimal cuts. Cuts and minimal cuts. Cuts and cuts and cuts. Cuts and minimal cuts. Cuts and minimal cuts. Minimal cuts. Cuts and minimal cuts. Definition. Definition. Let G comma K be the transport network. Let G comma K is transport network transport network. Transport network with sources and sink D. With the source S and sink D. Sink D. Source S and sink D. Suppose that X is a set of vertices. Suppose that S is a suppose that X is a set of vertices set of vertices such that S belongs to S belongs to X belongs and D does not belong to X. And D means sink does not belong to X. Does not belong to X. And X bar denotes the complement of X. X bar denotes the complement of X. Complement of X. Complement of X. In VG. Then the set of X and the set of X comma X bar of all edges X comma X bar of all edges from a vertex in X. From vertex in X to vertex in X bar to vertex in X bar. Vertex in X bar is called SD cut. Is called SD cut. SD cut means source and sink cut.